this unit has to do with calculating average atomic masses. If you actually look at the periodic table and you're focusing on carbon, for example, a carbon atom that has 6 protons and 6 neutrons, we would add it up to have a mass of 12. Protons have a mass of 6, and neutrons have a mass of 6 total, because there's one each. So that comes up to 12. If you look at the periodic table, you see this. So why isn't it just an even 12? Now, the most common guess on this are, oh, they added the electrons in. Well, electrons are so small that they're really not even affecting these decimal places because they're so tiny. So this actually isn't a whole number because it's actually representing different isotopes. So what you kind of have to think about is if you actually went outside and you picked up a lump like this, okay, this is just a lump of copper. There's a lump of carbon. There's a whole bunch of different carbon atoms in here, okay? And these black carbon atoms are just regular carbons. Well, a few of those carbons showing in red, because they're actually carbon 14. So we have carbon 12, and we have carbon 14. In a typical sample, the carbon 14 is just distributed throughout it. So when we do math, we want to actually account for the fact that we're looking at really an average of all the carbons in that sample, not the individual carbon atoms' masses themselves. A nice example to look at is the example of people's ages. So this example kind of makes me look old, and right now a little bit crazy because I'm actually by myself, so I'm just making some stuff up. So typically what we do in class is we go around the room. So I'm going to collect some ages from some imaginary students. So most of the time when I do this activity in the beginning of the year, most of my students are 16. A few have not turned 16 yet. I might have a 15-year-old or two hanging around. Some are a little bit older, occasionally a senior taking the class, and then there's a 36-year-old. I don't know who that could be. So the number of people that I'm including in this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 imaginary people in this room. So if I actually wanted to calculate an average for the age of all of these people, what I would do is I would add up my ages, so 16 plus 16 plus 15 plus 17 plus 17 plus 18 plus 16 plus 16 plus 16 plus 16 plus 17. So our typical way of calculating an average, we'd say 180 divided by 12. The average age of people in this room is 15. Now, it seems a little strange because we really expect this to come out a little bit closer to 16, but this is a... Sorry for the pause in the action there. I was forgetting to add in the 36. So if we add this up with the 36 in there, because I am a person in the room, and then I divide by 12, I actually get an average age of 18. Now, this is pulled up a little bit by my age, and this is also pretty representative of, fairly close to how old most of you are. Sorry, fairly close to how old most of you are. So when we look at this, it does not represent me. I'm nowhere near 18, and some of you are not 18. But it's a pretty good, demographic descriptor of about how old most of you are. There are other ways to calculate an average. So another method of calculating an average that we can actually do using those same numbers. 6 of the people included in that were 16-year-olds. So if we look at our numbers back here, we have our 1, 2, 3, 4, 5, 6, 16-year-olds. Out of 12 people, that's half of them. So I can call half 0.5, and I can say 0.5 of my people are 16. 3 of my people were 17. That's 0.25 of my people that are 17. I'm kind of looking at these like fractions, 50% or a quarter. I have one 18-year-old, it's about 0.8%, one 15-year-old, and one 36-year-old. So you can see by looking at these that we expect the numbers that are represented the most to be 16 and 17. do have some outliers like 36 with a huge number pulling it up, but 15 is kind of pulling it down. But those kind of in a way essentially cancel each other out. So if we take a minute and we punch each of these into our calculator. So we punch each of these into our calculator. We multiply them. We actually get proportions of our final answer. And if we add all these together, this will tell us the actual average age. And that gives us 17.77. Now, you would never actually sit down and calculate your average this way. This actually came out a little bit more accurate. There's really some rounding error in it, but you'll see 17.77 is pretty close to 18. So usually it's easier to just add things up and divide them by the whole. The problem with when you have a sample of atoms is you can't divide by the whole number of atoms because it's too big of a number. So we do things based on what are called relative abundances or percentages. Another place you've seen this is with calculating grades. So if the grading percentages for a class are 50% quizzes, 40% tests, and 10% labs. So if you had a student with a quiz average of 85, you'd say, okay, 85% from quizzes, so 0.5 or half of the grade is comprised of that 85 quiz average. I'm going to add that to my test average of 73, and that's a large chunk of my grade as well, so 0.4 times 73. And then finally, I have a lab average of 100, which is awesome, but guess what? Labs don't count for that much, so they're a pretty low portion of our grade. So we do 0.5 times 85. So you can look at this and say, okay, 42.5 points out of that possible 100 points is comprised of test grades, or I'm sorry, quiz grades. 29.2 more are coming from test grades. And 10, which is really the maximum amount you can get from labs, are coming from labs. So I do 42.5 up to 29.2. This is a simplified version of, really what's happening in my gradebook. So my gradebook is actually taking all the numbers that are plugged in and figuring out these averages. And my gradebook would tell you have an 81.7, which good news will round up on my gradebook to an 82. Or, I'm sorry, not my gradebook, school tools will round up to an 82. So you can see that even though you got 100 for the labs, that didn't really pull you up that much because that's such a small portion of the grade. What really most affected the student's grade were really these quiz grades right here. But they were helped out by that lab. That lab, did pull them up a little bit. But even if they'd done, a little worse in their labs, it really wouldn't have broken the bank. So what we're doing when we calculate each of these is we have to really take into account that we're going to have different numbers of protons and neutrons. So this graphic kind of illustrates when we have all the same isotopes there, that's not really, it's not particularly helpful. I'm going to skip this. So we're going to do a relative abundance calculation like something you would see on a Regents exam. Chlorine 35 isotopes. So this 35 right here is talking about our mass, and it has a relative abundance 75.77. Chlorine 37 with a mass of 37 has a mass or an abundance of 24.23. So to calculate the average atomic mass, first thing I want to do is change my percentages to a decimal. And this is a simple loop. I'm dividing by 100. Now I'm going to take each of those masses and multiply it by my abundances. So I'm going to do 35. My isotope that has a mass of 35 has an abundance of 0.7577. I'm going to add that to 0.2423. I don't know why I wrote that decimal place twice, but fix that. Multiplied by my mass of 37. So, looking at this, you're going to notice more of the chlorine has a mass of 35. Your average here, so the average of all the chlorines, if you think about it, should fall somewhere between 35 and 37. And it should be a little bit closer on the 35 side. So you're going to punch both of these in. We're going to do 35 point. I'm just checking my math here. I've had a long mistakes in this video. Don't want any more. So we should come out with an average of 35.486, which we're going to round this down a little bit and call this 35.48 and use. So you are going to notice that it's between 35 and 37, and all sorts of issues here. It is between 35 and 37, and it is a little bit closer to 35. Our alternative setup here, a lot of people like to do this way, rather than worry about changing your decimals, you can simply say 35 times 75.77 divided by 100, 37 times 24.23, and divided by 100 in this step. And remember, you're always thinking at the end, you're going to get the same thing for this, you're going to get your 35.48. You're always thinking, does my answer make sense? Yep, it's between 35 and 37. Yep, it's closer to 35. So Spencium is a very important isotope, a very important element. It has a couple of different naturally occurring isotopes. Spencium-33 has a relative abundance of 35.6. Spencium-35 has a relative abundance of 5.8%. Spencium-36 has a relative abundance of 58.6%. So my first step, I'm going to actually go and take each of my percentages, put them into decimals. Be very careful when you have single numbers there. You're moving the decimal twice, remember. In step 2, I'm going to multiply these. So first I'm doing 0.356 times 33. That's the abundance for that particular isotope. I'm going to add that to 0.058 times my abundance of 35. And last but not least, 0.586 times 36. Now, at this point, I always like to kind of take a little pre-solving step and say to myself, what do I expect to get here? My final answer should be between 33 and 36. What should it be closer to is a little bit hard to tell here because we have more numbers, but really the reason I like to think about this, a lot of people want to divide again at the end, and you really don't want to do that. You won't get anything around 33 to 36 if you divide again. Just take a minute and calculate these and check your answer. So you should have gotten 34.874 atomic mass units. Again, the AMU is the atomic mass unit. That is our unit that we use for things in the actual atom. Now, if you think about this, think about if your answer makes sense or not. This is between 33 and 36, so it's a great answer. It is a little bit on the lower side, which for the most part makes a decent amount of sense because 33 is so low, we have a decent amount of that. Just take a minute to solve each of these problems and then check your answers. So you can go ahead and check your answers. Subatomic particles, remember, you need to be referencing protons, neutrons, and electrons. Not okay to say mass. They're different because they have a different number of neutrons. Best answer is really protons for your similarities, but electrons is okay as well. This is the dot structure for your dot diagram for your atom. So you have 6 valence electrons. This 33 right here is distractor information. It's just telling you the mass. You don't need to know that for Lewis dot structure. Be very careful with moving your decimal places and some of these smaller ones, like 0.76, for example. Remember, you're going to move that and actually have 0.0076. This guy's going to get moved to be 0.0002. So you have to be very careful. Also, with these, when they give you the full atomic masses, you're using those. Copper question. Your copper 65 has more neutrons. You can tell how many neutrons each one has. Because it's asking in terms of subatomic particles, you do not want to just say that they have different masses. Their number of neutrons, so it makes them different. Their protons and electrons are the same. This is distractor information. 65 here, this has to do with the mass. Your electrons, remember this is an atom. So protons equal electrons. So you have to look up 29 protons on the periodic table. It's a bit of a trick question. And then last but not least, remember you're using these full masses given to you on the table, and you changed your percentages into decimals.